Hello all. So today I, Manak Saha, am going to speak on the microstructure evolution and the mechanical response of nickel-alloyed FeMnAlC steel. So initially I'll be describing the motivation and objectives of my research work. The material of interest is basically the hot rolled 5 nickel-alloyed iron 16 manganese 9 aluminum 0.9 carbon, all in terms of 8% steel. So now if we look at a typical engineering stress strain diagram obtained using uniaxial tensile deformation of an aluminum alloyed FeMnC steel with this composition, so we would typically observe that this steel with a three-phase microstructure comprising of a gamma matrix plus the BCC plus the kappa phases shows an ultimate tensile strength of the order of nearly around 800 MPa. So now when we further add 5-8% nickel to this particular steel composition, so what we can clearly observe is that we have the ultimate tensile strength increased by nearly around 50% with a limited loss in terms of ductility when compared to that without nickel, of course. So now this means that when we add nickel, we have a strength increase. Now the question is, why is the strength going to increase then? Or why is the strength increasing? To understand that, we have initially embarked upon performing the thermodynamic analysis or the thermodynamic calculations by varying the weight percent of nickel in this particular system. And what we can clearly observe is that the addition of 5-8% nickel, or rather to say in general, the addition of nickel basically leads to the stabilization of the B2 NiAl phase in this system as predicted thermodynamically from here. And this is very much in contrast with the 0-weight% nickel, where we can clearly observe that the typical microstructure with 0-weight% nickel would not show a B2 phase at all. And also the same can also be inferred from the thermodynamic predictions here. So now this means that it is very interesting to now investigate the evolution of the B2 phase in the microstructure. So to this end, the objective of my research work that we have designed is to investigate the nickel-induced B2 phase evolution as a function of annealing temperature, where annealing was performed at a wide range of temperatures ranging between 500 to 1200 degrees anneal condition. And what we can clearly observe that if we look at at a temperature of nearly around 500 to 600 degrees, we can clearly observe that we have the gamma plus the kappa plus BCC plus the B2 phases thermodynamically predicted to be stable. Then when we look at a temperature of nearly around 700 degrees, we see that we have the gamma plus the kappa plus the B2 phases shown to be stable here. Then when we look at a higher annealing temperature, we have only around 900 degrees, we see that only the gamma and B2 phases are shown to be thermodynamically stable. Whereas at a narrow phase field around 1110, we see that the gamma plus BCC and the plus B2 phases are thermodynamically predicted to be stable. And then at a temperature of nearly around 200 degrees, we see that only the two phases, that is namely the gamma plus BCC phases, are thermodynamically predicted to be stable for the 5-8% nickel addition. So now with this, we have further studied the influence of the nickel-induced phase evolution on the mechanical response. So now, with a brief introduction about my research, and also the material of interest, I'll now be discussing about the bulk phase analysis that we have initially performed using the XRD, or the X-ray diffraction, as a function of the C2 annealing temperature. And we can clearly see from the as roll to the other annealing conditions, we see that the presence of the peaks corresponding to the presence of the gamma plus the B plus the kappa plus the BCC phases. So now when we perform the ACM-based microstructure investigations in the different conditions, so from the EPSD-based IPF map, what we can clearly observe is that we have a random orientation of both the gamma and the BCC grains. Now the corresponding phase map shows that the gamma is the majority matrix with a volume fraction of nearly around 92%. And also that now when we correlate the information from both these maps, we can clearly observe that the BCC has a banded morphology and mainly present along the gamma grain boundaries, and besides, it is also elongated along the rolling direction. So now with this, we have also further performed the ACM EDS analysis in the as-rolled condition, and we can clearly observe that the gamma phase has got a the majority matrix is enriched in manganese, whereas the BCC phase is enriched in aluminum and nickel. Now the same information can also be inferred from the EDS line scan, which is performed across the gamma BCC region, where we can clearly see the the trend that manganese is relatively enriched in gamma phase, whereas aluminum and nickel are relatively enriched in the BCC phases. In the BCC phase. So now the interesting question is, we have already seen the presence of peaks corresponding to the presence of the gamma phase in the XRD patterns, but from none of the SEM-based microstructure investigations do we see the presence of the kappa phase at all. This means that we need to have a better understanding of the chemical partitioning information in the gamma and the BCC phases separately. So, for that, we have embarked upon the site-specific 3D APT analysis, initially in the as-rolled condition. And what we can clearly observe that from within the gamma phase, we have the localization of the nanoscale kappa precipitates of average size nearly around 50 nanometers evolved within the gamma matrix, whereas from within the BCC phase, we have the evolution of the nanoscale B2 precipitates of average size nearly around 3.5 nanometers localized within the banded BCC structured regions. So now, for having further performed this investigation in the other annealed conditions, we have so this particular plot shows the variation in terms of the precipitate size of the diameter, their volume fraction, and their number density as a function of the annealing temperature for the kappa and the B2 precipitates. And what we can interestingly observe is from the as-rolled to 600 degrees to 1110 degrees, we see that there is an increase in the size of the B2 precipitates with a decreasing volume with a decreasing number density, which implies that we have the coarsening of the B2 precipitates between these three between the as-rolled and the 1110 degrees annealed condition, whereas on the contrary, when we further expose the material to a higher annealing temperature of 1200 degrees, we see that there is a decrease in terms of the B2 precipitate size or the diameter, but with a concomitant increase in terms of its number density, but still localized within the BCC phase. So this means that there is a disintegration undergone by the B2 precipitates from the 1110 to the 1200 degrees annealed condition. So now, having now known this, when we investigate the composition of the B2 phase in all these four different conditions, what we can clearly observe is that the B2 phase remains stoichiometric at the low annealing temperatures. That is, particularly to say, that is at as-rolled 600 degrees and 1110 degrees annealed condition, whereas a typical 1:1 stoichiometry is attained in the 1200 degrees annealed condition. Now the question is, so then in that case, how do we ascertain the presence of B2 phase then in the microstructure? So to do that, we have performed the Sachs analysis or the small angle X-ray scattering experiment in the three different conditions, that is in the as-rolled, the 1110 degrees and the 1200 degrees annealed condition. And these are the Sachs-based intensity profiles shown as a function of the scattering vector, where the arrows pointing towards the humped regions basically indicate the presence of some precipitate. And when we further perform the volume distribution analysis in these three different conditions as a function of the particle diameter, what we can clearly see is that based on these peaks, that we have the two different types of precipitates in the as-rolled condition, whereas only one type of precipitate is present in each of the 1110 and 1200 degrees annealed condition. Now, based on this information, when we further estimate the size of the B2 precipitates and plot it as a function of annealing temperature and compare the same with the APT-based sizes of the B2 precipitates, we see that there is a reasonable agreement in terms of the B2 sizes between the APT and the Sachs analysis. Now, this implies that the stoichiometric NIAL observation in APT at the low annealing temperatures basically corresponds to the B2 phase. So then, having now known this, I'll be further discussing about the contributions of the different phases towards influencing the overall strengthening. So if we, say for example, if you look at a 600 degrees annealed condition where the dotted horizontal line represents the uni-axial tensile yield strength, so what we can clearly observe is that the sigma A1 here basically represents the solid solution strengthening contribution from the gamma phase, and then the sigma kappa here represents the strengthening contribution from the nanoscale kappa precipitates localized within the disordered gamma phase. Then the sigma A2 represents here the solid solution strengthening contribution from the disordered BCC or the A2 phase, and the sigma B2 here represents the strengthening contributions from the disordered, from the B2 precipitates localized within the BCC phase. Now, when we further try to validate these results based on finding out the values of the sigma gamma and the sigma BCC based on their nano indentation hardness, we can clearly see that the gamma contributes nearly around 638 MPa to the uni-axial tensile yield strength, whereas the BCC contributes nearly around 1.1 GPa to the uni-axial tensile yield strength. So this implies that the BCC is the strengthening phase in the system. Now, what about the strengthening at the interfaces then? So for that, we have embarked upon correlative interface analysis at a near atomic scale using the correlative TKT-APT approach. initially without tracer addition, where from the correlative analysis, we can clearly see that there is no preferential solute segregation at an FCC grain boundary. And similarly, this means that we have to now add a tracer element which should have a strong tendency towards undergoing grain boundary segregation. So when we now perform the similar experiment with tracer addition, where we have used oxygen as a tracer with a low solubility limit in alpha iron even at an elevated temperature. So what we can clearly observe is that the BCC is, the grain boundary is enriched in, we see a clear segregation of oxygen at a BCC grain boundary. So now with this, having seen this, we have used the Gibbs adsorption isotherm to find out the value of tau gamma, which means now the tau gamma here, which represents the change in the grain boundary energy due to oxygen segregation at a BCC grain boundary, for example, and that's equal to 9 minus of 355 nearly millijoules per square meters. So this this magnitude of tau gamma is much smaller when compared to that of soft metals, for example, aluminium and even other iron-based multi-component systems. Now this implies that there is a negligible influence of different interfaces towards influencing the overall strengthening. So now with this, I would now move towards with the conclusions of my today's talk. So the kappa is localized within the gamma phase, while B2 is localized within the BCC phase. Then the B2 portioning is controlled by the partitioning of nickel. The BCC is the strengthening phase, leading to an ultimate tensile strength of nearly around 1.2 GPa. Then the interfaces play a very negligible role in strengthening. And finally, that the addition of 5% nickel, as you can see from this particular plot, leads to nearly around 33 and 43% enhancements in terms of the yield and ultimate tensile strength, respectively, in the FeMnAlC state. So with this, I'd like to thank my research supervisor and also all the other members of the group and also all the other members of the National Facility for Atom Probe Tomography. So thank you for your patience.